Welcome you all in the lecture number 11 of Abstract Algebra MTL 6051. In this lecture, we will going to discuss the proof of class equation, first class equation and second class equation and examples related to the class equations. First, let us see what is the class equation and proof and its proof. If A belongs to G, what is A? A is element of G. And G is finite group. Remember that this class equation is applicable only for the finite group. Then order of CLA is equal to order of G by order of NA. What is NA? Right? Previously we not studied what is NA. Right? But we know that what is CA? What is CA? Centralizer of element A. Okay. This NA is nothing but the centralizer of element A, but NA is known as normalizer of an element A. Right? And define as just like CA. This NA is equal to X belong to G, it containing all those elements of G which commute with A. AX is EXA. And this is called normalizer of element A belong to G. Right? This normalizer is also known as centralizer. This is the statement of the theorem. Means order of CLA is equal to order of G divided by order of normalizer of A. Okay. See the proof. What is G? G is finite group and A belong to G. Okay. This centralizer or normalizer is subgroup of G. This we already proved. This NA is subgroup of G. Subgroup of G. Okay. NA is subgroup of G. Then this G can be written as union of, right? G can be written as union of right cosets of NA. If G, this G can be written as union of right coset of NA. Okay. See, this G is equal to union of I is equal to 1 to T N of A EXI. Okay, this is right coset and their union is equal to G. Suppose such type of coset is T. Right? Suppose such type of coset is T whose union is G. Okay, this thing. Then this order of this G, we know that every coset containing same number of elements. Then every coset 1 to T containing same number of elements. Then order of NA in multiplied by T is equal to order of G. Okay. Now let us suppose a set. What is the set? Set is S. Okay. Set is S. S containing this type of element. X1 inverse AX1, X2 inverse AX2, XI inverse AXI, XT inverse AXT. This S containing this type of element. Okay. Then all the elements of S are distinct. Suppose all the elements of S are not distinct. Then there are two elements which are equal. Suppose Xi inverse AXI is equal to Xj inverse AXJ. Then this can be written as, right? See here, Xi inverse AXI is equal to Xj inverse AXJ. Operate EXI both side from left side. EXI this thing and xi this thing. This xi and xi inverse is identity. Then the left hand side becomes axi and right side becomes xi xj inverse axj. Now operate xj inverse from the right side, that is axi xj inverse is equal to xi xj inverse a xj xj inverse. This is identity. Then this axi xj inverse is equal to xi xj inverse a. Okay, this thing. This implies that xi xj inverse belongs to Na. Since Na containing all those elements which commute with this xi xj inverse commute with A. This xi and xj inverse commute with A. It means xi and xj inverse belong to Na. And this shows that Na xi is equal to Na xj. Right? Hence, if any two elements are equal, means their cosets are equal. It means all the elements of S are distinct. Okay. Now we have to show that S equal to CLA. It means two sets are equal. A equal to B if and only if A is subset of B and B is subset of A. Now if S is equal to CLA, then S is subset of CLA and CLA is subset of S. Okay. First, let us see. S belong to capital S. And what is S? X1 inverse AX1, X2 inverse AX2 dot dot so on, XI inverse AXI and XT inverse AXT. This is S. And what is small s? Small s is element of capital S. If this small s is element of capital S, then this S must be equal to any one of these elements. Okay, say this S is equal to xi inverse axi for some I. It may be either equal to x1 inverse ax2 or it is equal to x2 inverse ax2. Means for some I this S is of this type. Okay. Then this relation shows that S is conjugate of A. Okay. What is B is equal to x inverse AX? It means B is conjugate of A. That is B belongs to CLA. Right? B is element of CLA. If S is conjugate of A, then S is element of CLA. See, what is S? S is element of S. And now what is S? S is element of CLA. It means S is subset of CLA. Say this is equation number 1. Okay. Now, let us assume that X is element of CLA. Then there exists G such that G inverse AG is equal to X, since X belongs to conjugate class of A. Therefore, there exists G inverse AG is equal to X. It means, what is G? G is element of G. And what is capital G? This is union of NaXi. I is equal to 1 to T. It means if G is element of capital G, then G is element of union of NaXi. Then this G must be belong to any NaXi. Right? Then this G can be written as one element of Na, say Y, and Xi. And this G is YXi. Then what is G inverse AG? This G inverse AG is YXi inverse. Right? This is equal to, see here, G inverse means YXI inverse A and G YXI, right? Okay, this YXI is equal to X inverse Y inverse by the reversal rule, A and YXI. What is Y inverse A Y? What is Y? Y is element of NA. It means AY is equal to YA. Since Y is element of NA, right? NA containing all those elements which commute with A, then AY is equal to YA. Then this AY can be written as YA, and this thing can be written as XI inverse Y inverse AY can be written as YA, and this is identity. Therefore, this is equal to XI inverse AXI, and this type of element is in S, right? This type of element is in S. Okay, then X belong to this. X belong to S. X belong to, it means CL is subset of, this is subset of S. Then from equation 1 and equation 2, CLA is equal to S. From equation 1 and 2 says that CLA is equal to S. Okay, S is equal to CLA. Then what is order of S? That is order of CLA, since both are equal. What is order of S? S containing T element. Remember that S is equal to x1 inverse AX1, x2 inverse AX2, so on, xt inverse AXT. This order of S is T. This is T is equal to order of CLA. Now, what is G? Order of G is T into order of NA. Right? Then what is T? T is equal to order of G divided by order of NA. Then what is order of CLA? This is equal to T. And what is T? Order of G by order of NA. In this thing, this implies that is, it is not clear. CLA is equal to order of G by order of NA. Okay. Now see the statement of first class theorem. First class theorem says that if G is finite group and A belong to G, then this thing we already proved that this is equal to order of CLA. Yes, we already know that. Previous two example I already solved on the basis of this. This is equal to order of G by order of NA, and G by NA is known as index of NA in G. Right? This statement is known as first class theorem. Now, what is second class theorem? In second class theorem, if G is group, then what is ZG? ZG is subgroup of G, with in fact normal subgroup of G. Then some element of A in G, it may be A belong to ZG. Maybe possible that A is also in center of G. If such thing happen, then second class theorem says that collect all the element of ZG. Collect all the element of ZG and order of ZG plus all the element of ZG, order of those ZG, and take the summation of order of G and order of NA only for those elements which are not in ZG. Take summation of this factor group only for those normalizers which are not in ZG. Right? This is the second class equation. Okay. Now see one example. If order of G is Pn, what is P? P is any prime number, right? What is P? P is prime number. If order of G is Pn, then Zg containing more than one element. Obviously, Zg always containing identity element, but if order of Zg is Pn, P to the power n, n is greater than 1, then this Zg always containing more than one element, right? See the solution of this on the basis of class equation. What is order of G? P to the power n. What is n? N is greater than or equal to 1. Okay. Remember the statement of second class theorem. This one. Order of G is equal to order of Zg plus summation of A does not belong to Zg, order of G by order of Na. Okay. What is Na? Na is subgroup of G. Okay. Na is subgroup of G. In fact, a normal subgroup of G. Right? But Na is subgroup of G. It means by Lagrange's theorem, order of Na divides order of G. Okay. Order of Na divides order of G. This thing by Lagrange's theorem. Right? Since G is finite group. And see, if G is equal to Zg, right? If G is equal to Zg, then what is order of Zg? Order of Zg is P to the power n. Since order of G is P to the power n, then theorem is this problem is solved. Order of Zg is greater than 1. Okay. But if G does not equal to Zg, it means there is any element in G, say A belongs to G, such that A does not belong to Zg. Right? Consider only those elements which does not belong to Zg. See here, A does not belong to Zg. Then, what is the order of Na? P to the power k. Okay? Order of Na is P to the power k. This order of Na is equal to P to the power k. Okay. Then what is the order of G by order of Na? This is P to the power n. This is P to the power k. And this thing is equal to P to the power n minus k. Okay. Okay. Now, it means order of G by order of Na is P to the power n minus k. And what is k? 0 is less than k is less than n. Okay. Then this P divides P to the power n minus k. That is P divides order of G by order of Na. It means P divides summation of order of G by order of Na. A does not belong to Zg. P divides this also. Okay. If P divides this and P divides order of G, right? If any prime number divides A and this P divides B, it means P divides A minus B also. Okay. If P divides order of G and P divides this, then P divides their difference also. P divides order of G minus order of G by order of Na for all A does not belong to Zg. And what is this? What is this bracket term? Bracket term is nothing but this is order of Zg. Right? This one is P divides, this thing is P divides order of Zg. P does not, it doesn't mean P divides Zg, P divides order of Zg. Okay? P divides order of Zg. From where you obtain is this from second class equation. If P divides order of Zg, then this thing says that order of ZG is greater than 1. Okay. This says that order of ZG is greater than 1. Okay. Now, let us see some more example related to second class equation and this problem. Okay. Now let us see another example. If order of G is P cube, right, and G is non-abelian group, order of G is this and G is non-abelian group, then what is order of ZG? Remember that if order of G is P to the power n is greater than or equal to 1, then order of such type of group and then order of ZG of such type of group is greater than 1. Okay, means ZG containing more than one element, right? What is ZG? ZG is subgroup of G. Then order of ZG must divides order of G by Lagrange's theorem. Okay, see the solution. What is order of G? Order of G is P cube. Then what is order of ZG? Order of ZG is greater than 1 by above example. Then what is the remaining choice of order of ZG? If order of ZG divides order of G, then it is either 1 or P square, right, or P cube. But this 1 is not possible by above problem. This order of ZG is greater than 1. This is not possible. Then P order of ZG is P cube. This is also not possible. Why? Suppose if order of ZG is P cube, right? This is also equal to order of G. Then G is equal to ZG. It means G is abelian, right? But it is given that G is non-abelian group. So this thing is also not possible. Order of ZG is greater than 1. This is also not possible. Then this is remaining two conditions. Now suppose order of ZG is P square. If order of ZG is P square, then what is order of G by ZG? This is equal to order of G divided by order of ZG. What is order of G? This is P cube. What is order of ZG? P square. We assume that order of ZG is P square. Then order of G by ZG is P. Then this G by ZG is isomorphic to ZP. Right? This implies that G by ZG is isomorphic to ZP. It means since ZP is cyclic, therefore this is cyclic group. And G by ZG theorem says that if G by ZG is cyclic, then G is abelian. What is G? G is abelian group. This is also contradiction since G is not abelian. Okay, so order of ZG cannot be P square. Then what is the condition remaining? That order of G is P. In this case, order of G is P. See another example. If G is any group, such that order of G is P square, then G is always abelian. Then G is always abelian group. Okay, this G is always abelian group. See the proof. If G is group, right, what is the possible order of ZG? Since order of G is P square, so the result says that what is n? N is equal to 2, which is greater than 1. Okay, then order of ZG must be greater than 1. Since ZG is subgroup of G, that Lagrange's theorem says that order of ZG divides order of G. Okay, it means order of ZG divides P square. Then what is the condition? This order of ZG is equal to P or P square. Okay, order of ZG is P. Then what is order of G by ZG. This order of G by ZG is P. Then this G by ZG is isomorphic to ZP. Then this G is abelian. Okay, G by ZG theorem. This G is abelian. And if order of ZG is P square, if this thing happen, then ZG is equal to G. Since ZG is abelian, therefore G is abelian. Okay. So any group of order P square is always abelian group. Now see, if G is finite group and order of conjugate class of any element A is 1, this happens if A belongs to ZG. Okay. Remember the second class theorem that order of G equal to order of ZG plus summation over order of G by order of NA for all those A does not belong to ZG, right? And order of G is equal to summation of order of conjugate class of A belongs to G. Now in this A belongs to G, there are two conditions. All those A belongs to G, but A does not belong to ZG, right? Collect all the elements which belong to ZG and all the elements which does not belong to ZG. Means if A is any element, whether it is in ZG, belongs to ZG or does not belongs to ZG. Collect such element. Those belong to ZG and those does not belong to ZG. And this summation bifurcate into two parts. For all those belongs to ZG, this is order of ZG. For all those A does not belong to ZG, for those elements, this thing happen, right? Now see the proof of this theorem. What is G? G is finite group. And what we have to show that order of conjugate class of A is 1 if and only if A belong to ZG. Now see, we already know this result. Order of conjugate class of A is equal to order of G divided by order of NA. Suppose order of CLA is 1. This thing is 1. Then 1 is equal to order of G by order of NA. Okay, that is order of G by order of NA. Okay, it means this A commute with every element of G. This thing says that if order of NA is equal to order of G, it means AX is equal to XA for all X belong to G. Okay, and what is definition of ZG? This is ZG. It means A belongs to ZG. That is order of CLA is 1, then A belongs to ZG, first part. And conversely, if A belongs to ZG, then we have to show that order of CLA is 1. Suppose A belongs to ZG. Then what is normalizer of A? This is nothing but whole G. Then what is order of G by order of NA? Both are same. And this is equal to 1. And what is order of G by order of NA? This is order of CLA. This is 1. Okay. Now, find all the conjugate class of S4. Remember that we already discussed about the partition function, right? Then what is the part for symmetric group S4? N is equal to 4. What is the partition of 4? 4 can be written as 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. Okay. These 5 way we can partition 4. Then P4 is equal to 5. It means conjugacy class of S4 is 5. Right. Conjugate class of Sn is Pn. Right. Now see. Corresponding to 1 plus 1 plus 1 plus 1, that is CLI, conjugate class of I, right? This is 1. 2 plus 1 plus 1, that is all the element in S4 of order 2, that is CL12. CL12 containing these elements 1 2 1 3 1 4 2 3 2 4 3 4, right? I hope you know all the element of S4, right? If not, go and see the previous lecture. Then CL12 is 1 2 1 3 1 4 2 3 2 2 4 3 4. What is 2 plus 2? 2 plus 2 is this type of element 1 2 3 4, right? See 1 2 3 4. Then this is equal to 1 2 3 4 1 3 2 4 1 4 2 3. And what is 3 plus 4? All the element of order 3 in S4, that is 1 2 3. This is conjugacy class of 1 2 3, and this one is conjugacy class of 1 2 3 4, this thing. Okay. Similarly, conjugacy class of S5, 5 can be written as 5 4 plus 1 3 plus 2 3 plus 1 plus 1, right? 5 can be written as 5. Then how many cycle of length 5 in S5? See the formula. This formula we already discussed, but see one more times. If n can be partitioned as 1 alpha 1 times, right, 2 alpha 2 times. So first see the example, then we will discuss this formula. Okay. What is the conjugacy class of S5? Conjugacy class of S5, all the element of cycle, all the element in S5 of length 5, all the element in S5, right, of length 5, that is cycle of length 5, that is factorial 5 5 to the power 1. Okay. Then all the element in S5, right, whose cycle length is 4, factorial 5 4 to the power 1. How many times 4 appear? 1 times. How many times 1 appear? 1 time. Then 4 to the power 1 1 to the power 1 factorial 1 factorial 1. 3 plus 2 factorial 5 3 to the power 1 2 to the power 1 factorial 1 factorial 1. Factorial 5 3 to the power 1 1 to the power 2. How many times 1 appear? 2 times. 1 to the power 2. Then factorial 1 factorial 2, right? Similarly 2 plus 2, 2 appears 2 times, 1 appears 1 time, 2 to the power 2 1 to the power 2, right? This is factorial 2 factorial 1. Solve this and sum all these elements, right? That is 1 10 15 20 20 30 24. This is equal to 125 120, and this verify class equation for S5. Okay. Now see the general formula. For Sn, n is greater than or equal to 3. N can be partitioned in this way. 1 to the power alpha 1, 2 to the power alpha 2, right, plus k to the power alpha k. Means 1 we have to add alpha 1 times, 2 we have to add alpha 2 times, and k I have to add alpha k times. Then order of CLA can be written as factorial n, right, 1 to the power alpha 1, 2 to the power alpha 2, up to k to the power alpha k, factorial alpha 1, factorial alpha 2, factorial alpha k. Okay. Now see one another important topic, that is silo subgroup. Before going to silo subgroup, silo group, not silo subgroup, silo subgroup is also there, but before going to silo group, we will discuss what is P group, right? Any group G such that order of G is finite. It means a finite group G is said to be P. Suppose order of G is 4 and 4 can be written as 2 to the power 2. Then this is 2 group. This is known as 2 group. Order of G is 9. This is equal to 3 square. Then this G is known as 3 group. Okay. If any group G whose order is P to the power n, then this G is known as P group. Okay. Order of G is 2 to the power 4 is called 2 group. Order of G is 3 to the power 6 is called 3 group. Order of G is 11 to the power 7 is called 11 group. Okay. See the Cauchy theorem. This is the only statement, but in later on, I will also give you the proof of Cauchy theorem. But here, I present only the statement. What is the statement? If G is any finite group and P divides order of G. Okay. G is finite group and P divides. What is P? P is prime number. Remember that P is always prime number. P is always prime number. If G is finite group and P divides order of G, then there exists at least one element A which is not identity. Their power is P is identity. Right? If G is finite group and P divides order of G, then there exists A belong to G such that A to the power P is identity. Okay. For example, what is order of G? This is 30. 5 divides 30? Yes. Then there exists at least one element in this G whose order is 5. Right? It is sure. There exists one element A whose order is 5. Right? This is Cauchy theorem. Now see, Cauchy theorem. This states that if G is finite group and P divides order of G, then G has an element of order P. Right? This and this both statements are the same. Okay. Now see, if G is finite group and P divides order of G, then G has subgroup of order P. Why? If A to the power, if P divides order of G, then there exists A belongs to G such that A to the power P is identity, then there exists a subgroup generated by A. Generated by A. What is that? A square, A cube, dot so on, A to the power P. This is identity. And this one is subgroup. And this subgroup is known as P subgroup. Okay. See, G be a finite group, P divides order of G, then G has a subgroup of order P. This thing, He has a subgroup of order P. See the example. If order of G is 27, 3 divides 27, then G has subgroup of order 3. Right? What is Silo first theorem? Silo first theorem says that if G is finite group and P to the power n divides order of G, okay, then G has subgroup of order P to the power n. G has a subgroup of order P to the power n. Okay, see, if order of G is 100, then 2 to the power 1 divides 100. Then G has subgroup of order 2. 2 to the power 2 divides 100. Then G has subgroup of order 2 to the power 2. 5 to the power 2 divide 100. Then G has subgroup of order 5 square. But remember that here P is prime. Here P is prime. See, here 2, 5 and these 2 all are prime number. Okay. What is silo P subgroup? Silo P subgroup is, in short form, we also denote as SST, right? Silo subgroup. Silo P subgroup is if G is finite group and P to the power n divides order of G, but P to the power n plus 1 does not divide order of G. Then the subgroup of order P to the power n is called Silo P subgroup or PSSG, right? Later on, we will discuss in our next lecture in brief, in details about the Silo first theorem and examples related to the Silo first theorem. Okay. After that, we will discuss what are the commutator, okay, nilpotent and other groups.